Hello. So we are back to our thermodynamic laws. So we talked about the first law of thermodynamics last semester that said energy was never created or destroyed, right? It changed form. It could go from potential energy to kinetic energy, but it is never going to absolutely disappear. We are always talking about a two-component system. We're always talking about what is the system and what are the surroundings that are compared to it. So if we were thinking about ice melting, I put ice on the countertop, it is going to melt, right? We know that at room temperature. This system that we are looking at what is happening to the ice. So that is our system. Everything else around that is the surrounding. So our countertop, the air, right? The dogs in the room, the people in the room, all of that is our surroundings, okay? What we really care about is what's happening to our system in comparison to those surroundings. Is energy going in or is energy being released? Okay, that was mostly our first law of thermodynamics, was talking about that change in energy. Our second law of thermodynamics, though, is talking about the entropy. So, the entropy change of the universe must be positive for it to be spontaneous. So, therefore, if we have a reversible process, our entropy change is going to be zero. If it is spontaneous, if it is automatically going to increase in disorder, our delta S is going to be positive, the delta S of our universe. So the thing though is we could have a positive delta S of our system and a negative delta S of our surroundings, right? Because one's going to increase in disorder, the other one is going to decrease in disorder. But overall, when you add them together, the delta S of the universe is always going to either be zero for a reversible process or greater than zero for an irreversible spontaneous process. Okay? If you get a negative delta S, you are wrong. It will never happen. We will never have an increase in order. Your room will never automatically go and clean itself, right? There will always be an increase in disorder of the universe. You can never win with the universe. So let's take a look at this following situation. So here is gas in a vacuum, right? It's under vacuum. We have four balls. These are four gas molecules. So if our stopcock is closed, right? They're all on the left over here. When we open our stopcock, there are three different energetically equivalent states. They could all be on the left, they could all be on the right, or we could have two on the left, two on the right. Those are all energetically favorable. Okay, either one, all of them are ideal. They all could happen, right? But one of them is better. One of them is more probable. Well, these are called macro states. So A, the macro state of A was all four of them are on the left. The microstate is that 1, 2, 3, and 4 are on the left. B, all four were on the right. So 1, 2, 3, and 4 in the microstate have to be on the right. But if we look at the macrostate C, where there were 2 and 2, it doesn't matter which two are on the left, which two are on the right, right? You could have 1 and 2 on the left, 3 and 4 on the right. You could have 1 and 3 on the left, 2 and 4 on the right, right? We have all these different combinations. We have 6 different combinations of these gas atoms, these gas particles. And so this one is a better arrangement, right? Because we have different ways that we can arrange them. It is going to have a better increase in entropy because the likelihood of us being able to get all four of them over here on the left is very difficult. It's a lot easier to get 2 and 2. So therefore, this is more an energetically favorable increase in entropy system. So the macro state that has the highest entropy will also have the greatest dispersal of energy. So therefore, C has the highest entropy. There is the highest disorder, right? These two are rather ordered. C is pretty disordered. So overall, when we talk about our change in entropy, we're talking about the final minus the initial. So this S could be S of the system. It could be S of the surroundings, right? It could be S of the universe. We have a whole bunch of S's this could be. But when we talk about delta S, it's always final minus initial. So our entropy change is favorable when we get something that's more random. So if our delta S is positive, that is a favorable entropy change. Let's think about the different changes in entropy we have. Well, we could have a reaction whose products are in a more random state. So we know if we look at a solid and a liquid, right? Solid is more tightly packed than a liquid. So we know that a liquid is more random than a solid. Same thing with a gas. A gas is more random. So going from a solid to a liquid to a gas would have a greater increase in entropy. Also, if we look at the number of moles of our products, so if you have more moles of product than you have reactants, right? That means we're making more things. And so it's going to be more random. So we would have a greater increase in entropy. If we have an increase in temperature, we know when we increase our temperature, things move faster. And so since they're moving faster, they can move past each other more easily. And so we have a greater increase in entropy. Also, solids going into ions, we know that, right, solids ordered, ions are disordered, and so we'll also have another increase in entropy. So if we look at our states of change, it's if something's going from a solid to a liquid to a gas. Well, what do we know? In a solid, these molecules are not moving past each other. All they're doing is vibrating, right? So they're vibrating in place, they're just staying there. If we have a liquid, though, they are still vibrating in place, but they can move past each other a little more freely. So we have some rotation going on. So that would be a more disordered system. Gases, though, right, they're just moving all over the place, floating, going wherever they want to go, right? Going past each other, hitting each other. So they're extremely disordered. So the delta S of our gas would be much higher than a liquid and is higher than a solid. So predict the sign of delta S for each system. A is going from a gas to a liquid. So it's going from disordered gas to a liquid, which is more ordered. So this would be a negative change in entropy, right? Because it's going from disorder to order. So that is negative. B, solid carbon dioxide subliming. Well, it's going from a solid, which is highly ordered, to subliming. That means it's becoming a gas, right? So it's going from a solid to a gas. Order to disorder. So delta S would be positive. If we take a look at C, well, all of them are gases, right? But one on the left, we have 2 moles of gas. On the right, we have 3 moles of gas. So which one do you think? Well, 3 moles of gas, right? It would rather be in 3 moles than it would be in 2, because 2 is more ordered than 3. And so this would also have a positive delta S. So make sure you go through, pause this video now, try this example, and figure out what is happening with each sign. So we are talking about heat transfer now. So what is happening in our system? So our second law of thermodynamics demands that the entropy of the universe is always going to increase for a spontaneous process. So if we think about condensation of water vapor. So when you go outside in the morning, isn't there a dew on the grass, right? And that is spontaneous. That's going to happen. You're going to wake up every morning and there's going to be dew on the grass. But water vapor is a lot more random than liquid water. So why would it want to go from the gas phase to the liquid phase? That doesn't make sense, right? Because that's becoming more ordered. So if a process is spontaneous and the entropy change is unfavorable, that means there must have been a large increase in the entropy of the surroundings. So the surroundings, when the surroundings lost those gas molecules, what did end up happening to the surroundings? Well, the surroundings increased in entropy because now all the other molecules in the air have a greater ability to move around, and so we have a greater increase in entropy of our surroundings. So since our surroundings entropy increased, even though our system's entropy decreased, overall, that means that the delta S was still greater than 0 of our universe. So the entropy increase must come from the heat released from our system. So the process must be exothermic. So this process was an exothermic reaction. Even though it decreased the entropy, it was exothermic, and so that overcame the entropy of the system. So when a system is exothermic, we know, right, it's exothermic, it's giving off heat. It adds heat to the surroundings. If it's giving off heat to the surroundings, the entropy of the surroundings is increasing. So it is becoming more disordered. If the system is endothermic, it takes in heat. So now your system has more heat, it has more disorder, right? And the entropy of the surroundings is more order. So the amount of entropy of the surroundings changes, depends on the original temperature. So if you think about it, if it went from something that's freezing, so if it went from 0 degrees to 10 degrees, well, that's a big difference because we know at 0 degrees we have water, is becoming a solid. At 10 degrees, it's a liquid. So that original temperature difference is it's a significant difference between water freezing and water liquid. So that does make a huge difference. But if we're at a high temperature, if we're at the difference between 100 degrees and 110 degrees, well, there's not much difference there because water is a gas in both of those states. And so we don't really care as much about the